Hello everyone, it is July 21st, 2022, time's about 17:15 out. It is Rant time, Rant number 172, and as promised, Bowen's reaction series. Now, this looks a little different than what many of you are used to, and that's fine. Take it in for a second while I grab my markers. I need to orient you here. Hopefully it won't take that long. I'm not going to get into, if you've never seen Bowen's reaction series before, I'm just going to cover this. This is my own chart. It is, some stuff is borrowed from other people's charts, but I tried to keep this as simple as possible. It's a conceptual model more than it is so it's qualitative, not quantitative as much. It assumes that your melt, your magma, whatever, is homogeneous, evenly mixed, has enough elements to do this whole thing, and isn't doing things like differentiating the chamber, stuff solidifies, settles to the bottom, isn't melting that country rock and incorporating it or anything like that. Let's get oriented real quick. For those of you that don't know, or those of you who are vaguely familiar, usually see as a Y diagram with a couple minerals and that's it. But my last GeoRant, here we have the continuous series. That's basically what I took you through. Your plagioclase becoming K-spar. As we go here, we'll get a little more into that here in a minute because there's some confusion there. Here you have your discontinuous series in blue, and here you have your residual, which is green. And if you notice, I've added these two zones here. This aluminum gumdrop zone, for lack of calling it anything better. Within here is where aluminum will start grabbing on to molecules and joining minerals as it cools into a solid. Above here, that doesn't happen. That's my ferromag zone. Olivine has no aluminum in it. It's too hot. There's, for that to occur. So you need the temperature to drop a little bit before that happens. Down here you have quartz. And to this point, you're outside the aluminum gumdrop zone just because you have no aluminum left to use. Everything else has hogged it up. Oh, Huck's in here too. So, continuous, residual, discontinuous. Residual is just your end game, if you will. Whatever's left, if you have all the necessary elements, you'll get muscovite and then quartz. Okay? There's nothing special about it, so we generally don't talk much about it. Your discontinuous series versus your continuous. Now, we'll touch on continuous because that's where some of the confusion was. Now, you guys have heard me talk about here. We just put calcium here in our melt somewhere. Calcium, sodium, and potassium. They're all throughout here just floating around. At 1200 C, calcium starts to form, solidify out, crystallize into anorthite, which is a plagioclase. All of our plagioclases go down to albite here. This is plag here, this essentially right there. And these two are our K-spars. And you've heard me say before, sanadine's a high temperature K-spar. But what happens here is a continuous series. There's a continuous reaction, but it's not continuous within these. It's not like calcium will just grab a sodium and there'll be a rearrangement or anything like that. That's not what it is. Continuously reacting with the melt, all right? So as anorthite takes up the calcium and our magma cools, it'll start to give some of that calcium back up to the magma chamber and grab sodium instead. We cool some more, same thing. Sodium is put back into the melt, and potassium, K-spars I was trying to say, starts being used by all of these things. Oh wait, no, sorry, no K there. Starts to be used by these other things. Okay, muscovite also has a lot of potassium in it, so it'll go here too when we get cool enough down here. Now, you may be asking, okay, that's nice, so anorthite gives up its calcium as it cools because it's in equilibrium, or needs to stay in equilibrium, and as the temperature changes, in order to do that, it needs to give up certain elements. Calcium is a group 2, potassium and sodium are group 1. Calcium is the only group 2 in this process. So as that cools, in order to get that equilibrium, it gives the calcium back up that it took. All right. and then, replaces it with sodium, which eventually gets back up in potassium. You may be like, well, Steve, well, what happens to all this stuff here? Well, obviously it crystallizes into other things, and other minerals can take it up. Now before I get into that, I'm gonna jump on our discontinuous series here. Discontinuous is different. It's not giving up elements like iron or magnesium for other things to use. These things don't have those atoms in them. What happens more or less is your olivine rearranges itself chemically, and I don't have it memorized, but your amount of atoms in there are essentially the same, but it gets rearranged, forming a different crystal, thus a different mineral. And you can see I have peroxine group here because there's so many. I'm not going to go through individual ones. In hornblende series, hornblende's an amphibole, but it's a series, so that's amphibole too. You could call it that. So your olivine eventually rearranges itself into peroxine. Now, I forget exactly which ones are involved here. I don't have all of them memorized, but while this happens, it'll start grabbing those other elements put back into it. I don't think calcium's here. I think calcium is lower, but like potassium, sodium, and things like this will get grabbed up. I think calcium is more like towards these this amphibole subgroup. It grabs most of the Na and Ca down there. All right, so then your peroxine groups become unstable at that configuration as you cool some more. So they change to amphiboles, hornblende series, right? Because hornblende is mostly what you're going to see. Now, as that happens and magma cools some more, you can go to biotite, or you can go right here. It doesn't really matter. You can see they're kind of along next to each other. If you have a lot of calcium, you'll form this amphibole subgroup more than you will biotite. But you have now rearranged those iron, magnesium, silicon, and oxygen atoms and grabbed more stuff as you cool. So eventually what happens is everything's used up, the entire chamber crystallizes, and that's how this whole thing works. Now, if you don't have certain elements, like if you don't have potassium, obviously you're never going to form K-spar muscovite, or, K-spar muscovite. Sorry, I almost said quartz. Quartz is pure SiO2. If you don't have any calcium, you're not going to get anorthite, or your anorthite, your bitownite, labradorite, andesine, things like that. You also won't get any of these subgroups here, okay? But, no melt is completely devoid of these things. And this is just the most used elements, the most common ones: aluminum, calcium, sodium, potassium, iron, magnesium, silicon, oxygen. We're not dealing with the minor stuff like uranium that'll form beta-light and zircons, or, titanium, or any of the other stuff. Yeah, that stuff's present too, and that's a talk for another time. It's not involved in this series here. Okay, so that's basically what happens. I think I've explained that. Your continuous is an exchange. As it cools, your crystals are essentially not that different, but they give up certain atoms back to that melt, which is used in other ones, as these rearrange their forms into different crystal structures and hog those up. There's something else I was going to mention real quick, and I don't remember what it was. Using this anorthite, trying to do this in one take, and then I get into my head and I get totally distracted here. The temperatures are about evenly spaced here. All right. Now, let's see. Now, if you have, just one thing. Some of you guys have talked to me about, or I've heard me talk about feldspathoids before, foids, and they're not anywhere on here. Your sodalite, stuff like that has a nice fluorescent orange color and hit with long wave UV. Those form usually in silica pore magmas. So you won't ever form these bottom things here. And you almost never get these too. So it doesn't matter if it goes down your magma temperature goes down to 600 degrees or not. You don't have enough silica to form these. It gets used up, and your feldspars will form along with voids, but they are also taking that stuff up. So as you get closer and you hit equilibrium sooner, you'll start getting feldspathoids instead of your muscovite quartz and your low or your cooler K spars. I think that's it. I'm not sure if there's anything else. I hope this clears something up. You know, I hope that does. I know it's a bit complicated. Like I said, this is for an idealized magma chamber, which never ever happens. You know, so you know, other things can happen. It doesn't differentiate between mafic, intermediate, or felsic rocks, but generally they are associated with temperature. I didn't put that here. You start forming your, I think your mafic, your mafic rocks first, then your intermediates like andesite, and then your felsic finally. So that is related to this as well. Try to think if there's anything else. Your ferromanzone I covered. This plagioclase. I'm sorry I'm doing this to you. I just know I had something in my head and I'm going to kick myself in the butt the second I turn this off and remember what it is. Oh, biotite's also referred to as black mica a lot, muscovite white mica, and it actually is a real easy way to tell them apart in the field if they're bladed. And I'm not going to get in any deep mineralogy here ever for you guys, like, you know, technosilic or phyllosilicates and things like that, because I want to show you bigger pictures here, and I want you to know that every magma chamber is going to try to do this because that's chemistry. But you know, you introduce things later or you heat it back up or whatever, this obviously gets changed. Oh, I remember now. A lot of times you'll see this in action. You'll get, and I have pictures of this in my lab book, that black one I showed you last time, it's not here. You'll actually see in a beautiful picture of a good like 2 millimeter crystal in there, white striated plagioclase with a red K-spar halo, because what happened is you had your plagioclase crystal forming, then the temperature dropped so drastically, so fast that potassium couldn't exchange with the whole thing, and you end up with this outer rim. That is actually pretty common, but we generally don't differentiate that under hand lens. That's hard to tell. If you look for the striations, you just assume it's plagioclase unless you have microcline, you know, the hatching. And then we have something very interesting, which I have talked about before, Rockakivi granites, where you have K-spar in the middle and a green plagioclase halo, usually green, that's usually oligoclase. I can never pronounce that. And those are harder to explain, if you will, but maybe I'll do a video for that for you sometime, because you're going from here to here. And one more thing I want to talk about: as your magma chamber cools, these, you know, stable. You know, you hit 900, this is your stable line. These are unstable. These aren't even crystallizing yet. But once this magma chamber solidifies, and on the Earth's surface, because we have oxygen in the atmosphere, things like that, this chamber gets exposed, your stability is the opposite of this. These is the opposite of your crystallization. I mean, you know, even it just happens in non-oxygen atmospheres, 2 to a degree. But so these crystallize first, but this is your most stable mineral. Quartz almost never chemically weathers. It usually mechanically breaks down. And muscovite's stable, orthoclase is stable, biotite less, you know, oligoclase, and these, your olivine, your anorthite, bitonite, pyroxenes are very unstable. And that's a good way when you're identifying rocks, is a lot of times you'll see them weathered on the surface. Say you have essentially a sphere boulder of granite, if you can tell where the mafic dark minerals, because they've weathered out. And that's also my Black Lab reference book. But anyway, I think that's it. Make this too long. If you have any questions or comments, please leave below, and I hope you learned something.